These data are from graphite or diamond samples, and what we would like to do is see if we can work out a D parameter for these Auger spectra. That is to say, we want to differentiate these data and then work out the separation of the maximum to the minimum for these peaks. So if we just do a differentiation using a Cette Golay, then we end up with a lot of noise, but the idea is to work out this type of distance here. So we're looking at 22 for this graphite sample, but we can do better than using the differentiation using Cette Golay if, rather than using a polynomial of degree 2 to approximate the data when we try and work out the derivative, we can create a background type which will use a polynomial of higher degree. So it's the polynomial regression type, and it uses the cross-section parameters, or at least it uses the first one, to provide a degree for the polynomial that will be used to fit the data. And you can see how well this polynomial is fitting the data by looking at the residual. And if I restrict the range over which the polynomial needs to fit the data, I can see how the residual improves as I shrink the interval. And if I just get this right, then I come up with a residual standard deviation that would be characteristic of pulse counted data which has been combined from a multiple detector system, so it's less than 1. So this is now a reasonable approximation to the data, and having done so, I can use an option on the test data tab which says differentiate synthetic envelope, and when I press that button I end up with a derivative, and where the synthetic envelope has been defined we get a well-formed derivative compared to what you're seeing here. These correspond to where no approximation was there, therefore you've got the differentiation of the raw data, hence you see the noise. And what we can do is create a background type here. Let's just turn off the residual and adjust the region limits so that it targets the data that have been differentiated nicely, and then we'll use the SP background type, and it will then indicate 2 points here. That's the largest maximum intensity, there's the minimum intensity, and the difference between these two lines will represent the D parameter, and it's 23.4. so this is graphite. We can go back and look at a diamond rather than the graphite. So this will do the same exercise again. We will create a polynomial regression type. It's still got the same cross-section parameter in the first parameter, so that's the degree of the polynomial. And again we can adjust the region limit so that the approximation, and that's a fairly good approximation of the data, perhaps a little bit more than you might expect, but it's within the region of what you would expect for these type of data. So having done so, let's put these two together, in fact, so overlay them so we can see both of these that now have a region where there's a synthetic envelope that has been calculated from this polynomial, and when I say differentiate the synthetic envelope, I'll now get two VAMAS blocks, one for each overlaid in the active tile. Let me go back here and I'll just propagate the region that I'd previously used for the SP background type. Again, I'll just turn off the residual so it's clear, and let's display both of these. So you can see now we've got 13.6, this one is 23.4. so this is a graphite and this one is the diamond.